Hi, everyone. I'm really happy to give this lecture on the earthquake-resistant design of steel buildings in the United States. Again, thank you, Ashwin, for inviting me to this, and I'm extremely honored to be able to do this. So, today I'm going to talk about how we actually design steel buildings for earthquakes in the U.S. And I'm talking as someone who does a lot of research on the topic, but I'm also involved in code development. In fact, I work on code committees that directly relate to seismic design of steel buildings. And so I'm going to talk a little bit about the principles that we use and also about some of the actual tactics and processes that we use to design these buildings. So I do want to start out by thanking a few folks. The first is the American Institute of Steel Construction. Obviously they do a lot of work in code development for steel buildings, but also I do want to thank Professor Mike Engelhardt at UT Austin and Trisha Clayton, who have developed some of the graphics in some of the slides that I will be showing you today. So again, I want to start by thanking those individuals. All right, so today I'm going to talk about a number of topics. And the talk is going to be largely conceptual. So I'm going to talk about some of the fundamental ideas that we use for seismic design. Just to let you know, I have looked at some of the other lectures in this series, including the one by Professor Ashwin. And I'm going to go behind the scenes of some of the things that he mentioned in his lecture, especially about ductility. And why we do some of those things, and what my perspective is on that. So again, I'll start with general principles of seismic design and the importance of ductility. I mean, I guess at this point, many of you are aware that we try to design our structures to be ductile. But then really, from a fundamental standpoint, what is the importance of the ductility? So I'm going to talk a little bit about that. Once I'm done with that, I'll get into talking about trade-offs between strength and ductility. And then once these basic concepts are out there, I'll talk about a couple of seismic systems. Okay, so I'll talk about concentrically braced frames and buckling restrained braced frames. But before that, I'll talk about moment resisting frames with some level of detail. And I'll talk a little bit about how we design the system and the kinds of things we have to think about also for connection design of these systems. All right, so some of these things we'll go through, and finally I'll have a slide or so about talking about performance-based earthquake engineering in seismic design. All right, so many of you have probably seen this type of seismographs. That's what an earthquake looks like, ground motion or an accelerogram, and usually the fundamental idea is that this kind of seismogram is applied to a building, right? So you get some acceleration at the ground, and then the building shakes back and forth. And how the building shakes typically depends on not just how the ground shakes, but also the building properties, including the mass, stiffness, and also the nonlinear and yielding properties on the buildings. All right, so that's kind of the overall picture, and many of you probably know about this. And when you think about what that actually does to the building, the accelerating masses in the building produce inertia or have inertia, and they produce forces that the buildings have to resist. Okay, so that's the idea. So the main purpose of earthquake engineering, or at least the way that we design them, is to essentially figure out what kind of forces or what kind of inertial forces should we actually be designing the members of our buildings for, okay, so that they can survive an earthquake. Okay, so that's the main idea. Okay, so that's kind of the basic idea. Everybody is think a little bit about the general principles of seismic design and the importance of ductility. Okay, so that's kind of the next topic, and I'm going to talk about that for several minutes. Okay, so the first thing that I want to talk about in the context of US design, and different countries have different philosophies about this, but in the United States, the way a large majority of buildings are designed for earthquakes is to prevent collapse in the extreme earthquake, which is likely to occur at the building site. And so when we say extreme earthquake, we typically define this in terms of a fairly low likelihood of exceedance, something like a 2% likelihood of exceedance in 50 years, or so something like, we call it a 2 in 50 earthquake. And for this level of seismic intensity, we want to have a fairly low probability of collapse, something like 10% or so. Okay, so the idea is to prevent the building from falling down. However, what is equally important, or possibly even more important to keep in mind, is that the objectives are nowhere to limit damage of the building, to maintain function of the building, or to provide for easy repair. So in some cases, for example, high value buildings such as, or high priority buildings such as hospitals and so forth, we would like to maintain some degree of function under intense shaking. But in general, the idea is not, is mainly to prevent collapse. That's kind of the main objective. And we're not explicitly trying to limit damage. Okay, and this is a really important consideration. And one might wonder why we're not really focusing on these. Obviously, more and more people talk about things like resilience and repairability and so forth, but that's not really what the code is focused on. The code is largely focused on public safety. Okay, and the idea there is that some of these other objectives are performance objectives, such as damage, function, and so forth, really are in some ways, I would say, economic objectives, and owners can kind of decide whether they want to meet those. In fact, if you want to do that, sometimes it can get really expensive to meet those objectives. And so we want to prevent collapse. Okay, so that's really kind of the main focus, which I want to talk about. All right, so if we're not trying to limit damage, if we're not trying to, or if we're trying to sort of not worried about maintaining function, then it means that we're willing to accommodate a large amount of inelastic deformation in the building. And the only reason we do this is that the cost of the building is manageable. Okay, if we want every building to remain elastic, all buildings will end up looking like nuclear reactors. Okay, we don't want that. We want buildings to also be reasonably affordable to build. So that's the reason that we're thinking about ductile behavior. Okay, now, so let's talk a little bit about designing for ductile behavior. Okay, now one of the things that I notice when people talk about ductility or ductile behavior is people think about ductility as being an inherently good thing. It's like, okay, you want a ductile building because you want the building to, just have ductility for the sake of ductility. So in some ways that's okay to think about, but really, why we want buildings to be ductile, there's actually like a much more fundamental reason. I want to kind of get to that. I just don't want to think for you to think about, we want our buildings to be ductile. I do want to understand why we want our buildings to be ductile. And that has to do with, what I think is a very important trade-off or a balance between the strength and ductility of the building, right? So to talk about that, let's first, get on the same page and define ductility. Okay, so in loose terms, ductility is the amount of inelastic deformation a building can undergo after it starts to yield. Okay, and here I'm talking about, a building, but the same concept applies to members, materials, and so forth. So, you start to get yield somewhere around here, and then you get a large inelastic plateau, right? And then we can think about a ductility factor, for example, which is a ratio of the displacement at failure divided by the displacement at yield. The larger the ductility factor is, the larger your ductility is. Okay, so if you have a ductility factor of 6, 7, 8, 9, you get a much more structure that is able to stretch much more without actually failing. Okay, and then this going downhill is failure of the structure. All right, so I'm going to talk next about why this ductility influences how we design the strength of the structure. Okay, but before we get to that, let's talk a little bit about what can actually compromise or limit the ductility of the structure. So usually, if you think about steel as a material, okay, steel as a material has an elastic limit or a yield point, and then it begins to harden. Really, if you can keep pulling on steel just as a material, it tends to harden almost indefinitely. However, what causes this plateau and ultimately this failure, or where it starts to go downhill, is either some sort of fracture or an instability. So fracture is obviously easy to understand. The thing breaks, Or you might have instability, which could be local buckling, it could be global buckling of a member, lateral torsional buckling, or it could even be something like a side sway instability or collapse of a structure. So usually when something quote unquote bad happens, your structures start to go downhill. All right. So now with these basic concepts, you've got the concept of ductility, you've got a concept of what actually causes the end of ductility. We can ask the fundamental question, what force a structure should be designed for? And so what it comes down to is, well, if you have a structure which is, let's say being shaken by an earthquake, a very simplistic way of looking at it is, let's say we have a response spectrum for that structure, okay, which plots the time period of the structures versus the SA value or the spectral acceleration, then what is the V we should use? Let's say you do this for a bunch of different earthquakes and you come up with some sort of a design response spectrum. One could say, well, if I know the time period of the structure, I can calculate the S sub A for that structure, which is spectral acceleration, and then essentially multiply that S sub A times the weight of the structure. Okay. So that's kind of a fairly simplistic way of looking at it. And if you design a structure this way, things are great, your structure will very likely survive the earthquake. However, the problem with this assumption, and it's not really a problem, but what's kind of inherent in this whole design process is that we assume the structure to remain elastic throughout this. Remember, the response spectrum is developed for an elastic oscillator. So what you have here is a structure that remains elastic throughout this process. However, in reality, you could have structures that have ductility. Okay. And like I said, some structures might have a lot of ductility, some structures might have a little bit of ductility. And the further you push this point out to the right, either by delaying fracture or local or global buckling or collapse, you increase the ductility or the ductility factor of the structure. So, okay, so you've got this ductility and you've got this whole thing with the response spectrum. And I'm talking about these two different things here. How are they related? What brings them together? Okay, so now here's a fairly simplified representation of, or a monotonic representation of how a structure might behave in an earthquake. Okay, things are a lot more complicated than this. And I'm not going to get into that, but the main idea here is let's just pretend that the structure is pushed monotonically in one direction. It's like, but many of the ideas that I talk about here can be translated to earthquake loading as well. Okay. So let's first imagine that we design the structure as per the response spectrum concept that I just talked about, which is you calculate the S sub A for an elastic response spectrum, you multiply that by the weight, and then you use that to calculate the design base shear for which you will design the structure. What's going to happen is, because you took the full elastic response spectrum, your structure is going to behave in an elastic way until you get to that force. And it's basically just going to be an elastic oscillator. It's going to be like a spring. That's how your structure is going to feel. Okay, so let's say that's one structure. But then let's say instead of designing it for the elastic strength, which means the strength you calculated based on the response spectrum, okay, let's say you now decide to calculate or to design that structure only for 75% of that, or 3/4 of that. So you're not designing the structure for the full response spectrum strength, but you're designing the structure for 3/4 of that strength. All right, so what's going to happen? Okay, so one might say, oh, you're designing the structure for lower load than what the earthquake can put on it. So the structure is going to fail. It's going to be a bad thing. All right, so let's see what happens. So what people started finding out, and this is sometime in the 60s really, is that if you design the structure for a lower load than an elastic demand that an elastic response spectrum would impose on the structure, what actually ends up happening is that if the structure has the ability to deform in a ductile way, in other words, if the structure just doesn't disintegrate when it gets to this point, if it has some ductility, you get to approximately the equal displacement as you would have gotten if the structure were designed for the full strength. All right, so the structure designed for this structure is designed for the full strength. Now I'm taking that structure and I'm designing it for 3/4 of the strength. What I find is that if the structure has this ductility here, it actually it gets to about the same displacement. Now there's like several caveats to this equal displacement rule, so-called, but by and large, what people have shown is that if you kind of reduce the strength of the structure, you still get to about the same displacement. All right, so let's kind of take this further. Let's now design the structure for half the strength. Okay, so now this is like a pretty big deal. Your structure, you said that it was going to be designed for a force of V, but now you're saying, okay, I don't care. I'm going to design this structure for a force of half V. Remember, if you do this in any other context, if you design a bridge this way, if you design any other kind of structural system this way, which is quote unquote load control, actually have a weight of a truck on a bridge, okay? And if you design the bridge for half the weight of the truck, the bridge will collapse regardless of ductility because you have the full weight of the truck on the bridge. However, when you're thinking about earthquake shaking, it's not exactly that. What ends up happening is, in this case, if I design the structure for half the full elastic strength, I still get to approximately the same amount of deformation as I did for my full strength structure. However, now the structure has to spend a longer time on this yield plateau. So if I look at the strongest structure, it basically did not have any ductility requirement at all. It could just be completely, at this point, it could disintegrate, you're fine. This structure now, it was designed for a lower strength. It survived as long as it had some ductility. Now, if I design a structure for even a lower strength, I find that it's going to survive as long as it has a little bit more ductility. Okay, so now as I go lower and lower in strength, I find the required ductility goes up. Okay, let's take this down further. I find that if I design a structure now to a quarter of the strength that I would have designed the structure for originally, the structure will still survive as long as it has this significant amount of ductility. Right. So this is a really important concept, because when you're thinking about ductility, the idea is that in a seismic context, okay, if you reduce the strength for which you design a structure, okay, the structure is still going to survive as long as you provide enough ductility to the structure. Okay. So the weaker the structure, the longer it needs to ride on this plateau. Okay. So effectively, you end up with this trade-off. So you could have a structure which is full strength, all right? And that full strength structure doesn't need to have any ductility. It could afford to be completely brittle. On the other hand, if you start making your structure weaker and weaker, you need more and more ductility. Okay, so what's the point of all this? Okay, the point of all this is that if, on the one hand, you could say that a weaker structure requires more ductility, but if you flip this argument around, you could say that if a structure has large ductility, okay, or somehow if we could guarantee a structure to have a larger ductility, we can actually afford to design the structure for a much lower force than we would have had if it had no ductility. Okay, and this is the important, or this is the most important point to make here. In other words, if I can somehow make my structure ductile, it can be designed for a much lower load. Okay, and if you think about it, this is a purely economical argument. In other words, I'm going to have to spend money in making my structures ductile. Okay, the structures don't become ductile by magic. However, if I invest some money in making my structure ductile, I can actually save a lot of money in making my structure weaker. Okay, because often when you're thinking about making your structure ductile, you're doing things like improving detailing, improving welding practices, these kinds of things. Okay, so things that might not be obvious why they're important, but when they increase ductility, they allow you to reduce the strength of the structure. And remember, reducing the strength of the structure is money, okay? Because you're actually designing a structure for a lower and lower load. All right, so the issue mainly is that you can either decide to invest in making a ductile structure, or you can decide to invest in making a strong structure. Or you can try to find a point somewhere between those two where you put a little bit of money on the ductility to make the structure ductile, and you get a discount on the strength for which you have to design the structure. Okay, so that's the most important concept here. A further thing that I want to mention here, which going back to my previous point, is that, again, there is nothing fundamentally good about having a more ductile structure. Okay, you could have a structure that looks like a nuclear reactor, which is designed for a really high lateral force, and it does not need to be ductile. Okay, it would perfectly survive the earthquake without any problems. The only thing is it's going to be very expensive. Okay, so the question is, given your local economics, given the labor market, given the material costs, given all these things, given your local loads, where do you land in terms of the most economic or the optimal design? Do you want a really high ductility system, or do you want a low ductility system? And again, the answer depends not only on your local labor market material costs, but also on loads. For example, if you have an extremely highly seismic region, it might actually be worth doing something like this because you're going to see an earthquake. On the other hand, if you have a very low seismic region, it's okay, because what's going to happen is that by the time you design the structure for gravity, you have enough lateral strength that you don't need the ductility, okay? Because there's this trade-off between strength and ductility, okay? So that's kind of the important thing. So anytime you hear about why ductility is important, this is the reason, okay? All right, so now the question is really, how do you design to make structures more ductile? Designing the structures to be strong, that's something that, you know, is pretty standard in structural engineering. But how do you design a structure to be ductile? So I'm going to touch upon a few things in this context. Okay, so in the US, we largely use two different design codes for the design of seismic systems. Okay, so the first is the ASC 7, and I think many of you are familiar with ASC 7. It's called minimum design loads for buildings and other structures. That actually tells us what loads we need to apply for the buildings. Okay, and then we have the American Institute of Steel Construction's AISC seismic provisions, or AISC 341, which actually tells us how we make our structures ductile. So the ASC 7 is applicable to all kinds of structures, okay, whereas the AISC 341 is applicable to steel structures. Okay, it's also interesting for just to keep in mind that, for example, the AISC and the ASC, they are not really governmental organizations. These are trade organizations. So for example, AISC is just a consortium of steel fabricators who get together and essentially provide guidance on how to design structures. Okay, so again, a lot of the code writing in the United States happens outside of the government. It's usually trade organizations and other independent bodies which write these codes. Okay, so coming back to what force we design the structure for, okay? Remember, we were talking first about designing the structure for SA times the weight, yeah? However, now, knowing that the structure is ductile, we can actually get a tremendous discount on how we design the structure. And this discount is this so-called R factor. So in other words, rather than designing a structure for the full strength, we now design the structure only for a fraction of that strength. Okay, that's the R factor. If you look at the R factors for various systems in the US, okay, and there's special moment frames, many of them you're kind of familiar with. These R factors range from 3 to 8, okay? And this is really important to think about, okay? When you think about an R factor of 8, what this really means is you're taking a response spectrum, okay, and you're designing the structure for 1/8 of the strength that your elastic response spectrum requires you to. So this is a pretty big deal. You're actually designing the structure for a very, very low strength, okay? This gives you a huge discount in the tonnage. So in other words, your structure, you know, just your member sizes become way smaller because you have this large R factor. On the other hand, it's important to realize that, you know, just dividing by the R factor is very easy, you know, just a simple division. But really what you're saying when you use the R factor is that you promise to achieve the ductility required so that you can use these discounted forces. So you can't use this R factor until you do a lot of work and spend a lot of money to actually make the structure ductile. However, hopefully that money isn't large enough to offset the discount that you're getting. So again, the idea is you get a huge discount on the forces, and then you have to invest that discount in the ductility. Different systems have different R factors. SCBFs have an R factor of 6. BRBFs also have an R factor of 8, very high R factors. And I also do want to talk a little bit about undetailed systems. Okay, and the idea here is that even if you don't do special detailing for your structural systems, you don't do anything fancy, just by the virtue of being like steel systems, we find that if you follow a typical construction procedures in the US, you end up with an R factor of 3, which means you can actually take your elastic demand and divide it by 3 to calculate your forces. So this is really important. Okay, these are essentially discount factors. Now, because the R factors give you such good discounts on the forces, we often tend to separate our lateral systems from the gravity systems. Okay, so I'm giving an example here. So in the US, especially in steel buildings, every beam and column that you have will not be a seismic system. So in other words, I'm showing you here these dashed lines. These are gravity columns, and these gravity columns are simply pinned columns that really don't participate in seismic action. They just kind of go back and forth when an earthquake happens. What you have here, the pink solid lines, are the lateral systems. So when the earthquake happens, you actually have all the force goes into these lateral systems, but the gravity systems don't carry any force. And this is actually another layer of economy, because you don't really have to go in and make every single system a ductile system, or even have to design it to carry seismic loads. You can only get to have some frames in an entire building. Sometimes you'll have a very large building, and you'll only have a very small number of frames in that building which carry the seismic load. And the reason that you can do that is that the R factor gives you such a large discount on the total force that you have to design these systems for. Also showing here another system here where you might sometimes arrange the system not on the perimeter, but you might arrange them in the core. So you might often have like braced frames and so forth arranged in the core of the building, and the rest of the columns in the building will be gravity columns. Here's some jargon. I don't think it's necessary to get into the details of this jargon, but the idea is that what ASC 7 really does is it actually enshrines this R factor into how we calculate the C sub S, which is the seismic coefficient to calculate our base shear. So the R factor is there, and this R factor, as I talked about earlier, is as large as 8. Okay, so that's very important. For those of you who want to learn more about seismic design or how the seismic provisions work, you could just do a Google search for the 2022 AISC seismic provisions, and it's free for download. So you can actually download the entire thing. It's a pretty large document, but again, it's fairly easy to read. So for any of you who are interested, this is a free download. All right, so now that I've kind of talked about some of the basics of strength and ductility and the trade-offs between strength and ductility, I want to talk about a couple of systems and then get into some details about those systems. So the first I'm talking about is moment resisting frames. Okay, so we do moment resisting frames quite a bit in the US, okay, on the West Coast. And it's basically just a fairly straightforward arrangement of columns and beams. Okay, so we've got columns and beams attached to each other with moment resisting connections. And that's what a typical moment resisting frame looks like. Okay, under construction, as you'll see, there is a fairly rigid connection between the columns and beams, and the idea is that the moment from the column gets transferred entirely to the beam, or moment from the beam rather gets transferred entirely to the column, and so forth. Here's a moment frame. You'll see a corner box column. So the moment resisting frames are very highly desired, largely due to their architectural versatility. So architects love them. Okay, that's mainly because you get these large open bays. You don't have any obstructions in the bays, and they're also very ductile. And they have been proven to be safe through many studies over the years. Okay, so a lot of architects love moment resisting frames, and they often get specified, especially when you need open bays. The big disadvantage of moment frames is that they tend to have fairly low elastic stiffness, and so often we have to kind of upsize a lot of members just to kind of meet serviceability requirements and so forth. Okay, so that's something to keep in mind. All right, so that's a little bit about moment resisting frames. So now when we're talking about developing ductile behavior in moment resisting frames. Remember, moment resisting frames have an R factor of 8, okay, which means we want these frames to ride that plateau for a very long time. And the reason we want them to ride that plateau for a very long time because they're actually getting designed for a really, really low load relative to the elastic response spectrum load, like 1/8 of that load, right? So to do this, we need to apply some basic concepts, okay? So the first concept is, again, Professor Ashwin has talked about some of these, is that you need to think about this notion of fuses, okay? So you need to think about certain elements. So there's three things you need to do. You need to think about certain elements and identify certain elements that will yield in an earth, okay? The reason we do this is, if we kind of don't know ahead of time where our elements are going to be yielding, we essentially have to design the entire structure to be highly ductile, which is just extremely expensive. So if we know where our structure is going to yield, okay, then we can really design that to be ductile. So that's number one. So we choose those frame elements or the fuses. You detail these fuses to be ductile or to sustain large inelastic deformations. And then you design all the other frames to be stronger than these fuses. Now, I remember this nice picture of the chain that Professor Ashwin showed in one of his lectures, where you had all these links, and then you had, a weak link, and the weak link should be the ductile link. Okay, so you don't get failure in the brittle link. So the idea is you have a weak link, which is ductile, and then you spend a lot of money on that weak link to make it ductile, where everything else is stronger. Okay? So in steel moment frames, we choose the ductile element to be the ends of the beams and the base of the columns. Okay, we have many choices. Okay, we could have the deformation to be in the beams, in the columns, in the panel zone, but we choose the deformation to be in the beams. And I'll talk a little bit about it later. Okay, and there's actually a very good reason why we do that. Okay, people like to say, oh, you don't want your columns to yield because columns, are the gravity path. I mean, okay, but really the reason that we want our beams to yield is that if we start allowing yielding in the column, we get what we call a soft story. So again, I'll show you pictures later, but the idea is that if we start allowing yielding in the column, all the deformation will localize in one story, okay? And so then you'll have to design that story to have just absolutely tremendous deformation capacity, because all the deformation is going to happen only in one story. If you have, essentially, if you form 4 hinges in a column, you turn that thing into a parallelogram. On the other hand, if you have hinges in the beams, you don't have hinges in the columns, you distribute yielding over the height of the building. And so you don't have to make every single connection as ductile. Okay, so it's kind of important to understand where some of these are coming from. Okay, so going back to the principles, choose the frame elements. In this case, it's going to be beams. Detail those beams to sustain large and elastic deformations, and then design all the other frame elements to be stronger than the fuses. Okay, so those are the principles, but how do we actually translate these principles or ideas into actual design rules? Okay, so there's a few things there. Okay, so the first is that, there's the first few things that you'll see here. The first couple of things are system design considerations. When I say system design considerations, I mean these are things that you will do in sizing your members. Okay, so this is kind of a traditional structural design. So I'll get through these in a little bit. But then the things down here are actually detailing considerations which guarantee ductility. So remember, you got to have the strength and ductility, and they have to be coordinated. So the first few things get you the right strength, and the last few things here get you the right ductility. Okay, so let's talk about the system design considerations first. So the first thing to remember is that we must use the R factor load, but we should use that R factor load only for the weakest link, that is the beams. Okay, so in moment resisting frames, we're going to use the R factor load or the reduced load only for the beams. Everything else is going to be stronger than the beams. And the way we do that is first we design the beams for that R factor load. Okay? And then we design the columns, the panel zones, and all the other parts of the structure for increased earthquake loads. Okay. And again, there's a lot of like mathematical detail to it, which I'm not getting into, but the main idea is that you want your beams to be the fuse. And at a structural design level, you do this by making sure that everything else is stronger than the beam. Okay? Again, if you don't make the beams strong, or don't make the columns strong, or you don't make the beams the weak link, you'll find that you will start getting soft story collapse. Again, there's nothing quote unquote wrong with soft story collapse, other than the fact that you have to accommodate all the deformations of the structure only in a single story, which makes it very difficult. You also don't want failure in your panel zones, okay? Although you can allow a little bit of inelastic action in the panel zones. So to kind of get this response, where you have yielding up the height of the structure, we actually do the strong column weak girder check, which I'm guessing you're familiar with too. Again, to make a long story short, there's a whole set of considerations which make sure that we force the hinges in the beams. Once we sort of talk about the overall strength and like sizing the members to force the hinges in the beams, we really have to make sure that the connections where you're going to get all the inelastic action are ductile enough. Really, there's two kinds of connections where you're going to get a lot of inelastic action: the connection between the beam and the column, and the base connections. Okay, so today I won't talk about base connections. However, I'm happy to talk to anybody about base connections if you want to send me an email or something. Okay? But for now, let's talk about the beam to column connections. So how do we make these connections ductile? What are the issues with this connection? And we spend a lot of time trying to ensure that we get the ductility we want. Okay? So the connection ductility is one part, but I also want to talk about the fact that in addition to connection ductility, there's a lot of thinking we do about factors such as using compact sections to delay local buckling, lateral bracing to avoid lateral torsional buckling, and so forth. Now, some of these things, when you're actually doing the design, might not seem to make sense because they're just very prescriptive look things and they make your structure more expensive. Okay. So for example, the use of a compact section, which means you are sort of have a B over T ratio that cannot exceed a certain value. It might seem like an added cost because sometimes a lighter section with a higher B over T can actually meet your moment strength requirements. But that's not permissible because that might not have the ductility. And remember, the reason you want the ductility is because you've already committed to designing the structure for a much lower load. So the moment you say that you're going to use an R factor of 8, you have to do all of these other things, even if they seem like they're pointless and expensive. And they're going to be expensive, but remember, you've got like a factor of 8 discount on the load. Okay, so that's why you're trying to do the ductility. All right, so in this lecture, I'm not going to talk about compactness. I'm not going to talk about lateral bracing, shear panels, and all of that. I'm going to talk a little bit about detailing of connection because that's kind of one of the most interesting issues when it comes to steel moment rates. Backing up, again, remember, we want to develop a very large amount of inelastic action in these connections. Usually, we want to have about 0.04 radians or so of rotation in these connections without failure. Okay. So between the 1970s to 1994, that's what a typical beam to column connection looked like before the 1994 Northridge earthquake. So you had a column, okay, you had a beam attached to the outside. The beam would be connected with a shear connection or a shear tab, and this would be sort of done in the field, okay? And then once the beam was shear connected, you'd have a welder, and the welder would kind of deposit weld in the flanges, okay? And the idea was, well, the shear tab would carry the shear, and the welds and the flange welds would carry the moment. So this seemed like a pretty good connection from a strength standpoint, okay? Just a little bit more detail of this, so you had the flange welds taking the moment, and then the shear tab taking the shear. There's a couple of other details that I want to kind of draw your attention to here. Okay, so one is what we call the backup bar. Okay, and one might wonder why I'm talking about all these details, but as you'll see, they're important. Okay, so the backing bar is essentially a little piece of metal that you attach to the bottom of your flange. What that backup bar does is essentially prevents the weld from dripping down. Okay, and the idea is you have a weld access hole here, so when you're kind of welding through the flange, you can kind of go through the web to to kind of complete your weld through the flange. Okay. Here's a picture of a lower flange, what it looked like, okay? So you'll kind of see the weld here, here's the flange. Here's what we call a runoff tab, and the idea here is you don't want the weld to kind of drip down from here, so that's why you kind of put a runoff tab, so you get like a full welded connection. So in concept, if you think about this connection, it actually makes a lot of sense, from a strength standpoint, okay? Your welds in the flanges are providing a good load path for the moment, and the shear tab or the shear connection is providing a good load path for the shear, so this connection should hold together. However, in the 1994 Northridge earthquake, we saw a number of fractures. It was pretty widespread, or failures of these connections, which almost all started at the lower flange weld. Okay, so here's just a couple of pictures. I'm going to show you some pictures. So, you basically had these fractures come up from the lower flange connection there. Here's somebody who's actually put their business card or visiting card in the little fracture to kind of show you where the fracture is. Here's another example of fracture. Okay, so again, this is the column, this is the lower flange of the beam, and you get a fracture. Here's another one. Okay, so this was really a wake-up call, and we suggested that just putting like a structure together, welding it together, is not going to make it ductile. You can actually get fractures even in steel. And there was a multi-million-dollar study that went on for many years to try to understand why these kinds of fractures happen. Okay? And there were a number of factors. Again, if you do a search for the SAC steel project, okay, you'll find literally hundreds of reports and papers written about the topic. There were a number of things, okay, that caused it. Number one was that the actual yield stress of the beams was higher than minimum specified. So you might think that that's a good thing, if the yield stress is higher. But on the other hand, this higher yield stress puts higher stresses in the weld, which happen to be less ductile. It kind of violates the concept of that weakest link, because now you think that your weld is stronger than your material, but now no, if your material is stronger, then it can actually fail your weld, which is the weak link. So again, having a stronger material may not actually be a good thing. Okay. In addition to that, there were a lot of welding practices and materials that were found to be deficient. And there was also connection design and detailing issues that were found to be deficient. So first off, the main thing that I think a lot of us did was we started requiring toughness rated weld materials for all of these connections. Now, many of you, I don't know, are familiar with steel toughness and fracture mechanics, but the idea is that steel can have like a yield stress and ultimate strength. Okay, that's what we typically use for design. However, these usually don't tell us how ductile the material itself is or how stretchy the material itself is. And so usually when we now design these connections, both the weld materials and the base materials for moment resisting frames, we require these to have a certain toughness. Now, the actual numbers I'm not getting into there, but the idea is we want that toughness. And I think this should be 70, not 700. Okay, it's like minus 20 and 70. Doing each of these things is again expensive. Requiring these things is expensive. Having these materials is expensive, but it again assures ductile performance. Okay, so you want to use materials that are toughness. For welding, there's a number of different practices that we have to do, and I'm not getting into it in detail, but the idea really is that a lot of the things that I showed you, such as these backing bars and runoff tabs, okay, each of these things create these little stress concentrations and cracks and flaws, which ultimately reduce the ductility of this connection. And so as per our new design guidelines, we actually have to do things like grind out or remove the backing bar, okay, or make sure that we actually have a full weld here with no backing bar, so there is no crack or there is no flaw. And all of these things are again expensive to do, take time. Okay, so again, just because a welded connection looks good, okay, and it has the strength, doesn't mean that it's going to have the ductility. And one might wonder why we need to spend the money on ductility. Is because if you spend a little bit of money on making this connection ductile, you get a huge discount on the force for which you design the structure. So your member sizes just go down by a large factor if you can assure ductility because of that relationship I showed you between the strength and ductility. Okay. So once we kind of understood this problem and realized that we wanted to make these connections ductile, people have now come up with different kinds of connections which offer really excellent performance. Okay, so you could do things like strengthen the absolute the connection region. So your plastic hinging the beam doesn't form directly at the welds, it forms at a distance away from the welds. That's what it looks like. Okay, and this is great because what ends up happening is if you see the paint flaking, that's where the yielding has happened. This is where the material is ductile, is actually elastic. You see that where the actual welds are, you don't get a lot of inelastic action, and this increases the overall ductility and performance of the connection. So again, there's just a tremendous amount of work that's gone into making sure that these connections are detailed and use the right material so that they can provide the ductility you need. And ignoring these things even a little bit can tremendously reduce the ductility of a structure. So again, going back a couple of slides, the difference between a connection that looks like this and a connection that looks like this is tremendous. Okay, a connection that looks like this is very likely to fail in a non-ductile way or a brittle way, but a connection that looks like this is likely to perform a lot better. Okay, and these little differences allow you to save a lot of money on the cost of the building. I want to point you to another reference here, which is AISC 358. This actually gives us recipes or very clear procedures for designing different types of connections that meet the ductility requirements for special moment frame application. Okay, so this is something that again is free for download. You could just download that, and if you just look at this, you'll be able to see how to make these connections ductile. And it's tremendously interesting, not only because it kind of shows that little things in these connection details can actually create a huge difference in how those connections actually behave. So it's also very easy to use. Okay, it's very prescriptive. If you just follow essentially the process here, you end up with a connection that is ductile, which allows you to use an R factor of 8 in some of these frames. Okay, so that was about SMRFs. I'm going to talk a little bit about concentrically braced frames, and I'll talk a little bit about buckling restrained braced frames. The basic ideas of trading off strength versus ductility are essentially the same thing. Okay, so you could have large strength, low ductility, or you could have high ductility, low strength. The concentrically braced frames are have a little bit lower R factor than SMRFs, which means they can be designed for a little lower strength, but then they need to have a little bit higher strength, but then they don't need to have as much of a ductility as an SMRF. The advantage of concentrically braced frames is that they tend to have very high elastic stiffness. Okay, the disadvantages is a little bit less ductile, but it doesn't really matter because you're designing them for a higher strength. However, the bigger problem with this is that you actually have reduced architectural versatility. Architects don't like that. Okay. Few things with CBFs, you could have single diagonal, inverted bracing, V bracing. For special concentrically braced frames, we generally do not allow single diagonal because they tend to kind of deform in one way versus the other because they're asymmetric response. But usually inverted V bracing or V bracing or two-story X bracing tends to be very popular for CBF type structures. I'm going to show you a few photos. Okay, so here's what a CBF looks like in the US. Again, I do want to make a few other points, is that if you look at the structure, okay, this entire building, you only see a CBF in this plane, and there's probably CBFs back somewhere there. Again, this highlights the point is because these are designed to be ductile, you design them for a low force, and so you don't need a CBF in every bay. So for example, these columns here that you're seeing in the back, they're not CBF, they're not even seismic columns, they're gravity columns. Okay? So more CBFs showing different configurations. Okay? The way we expect the CBFs to behave under earthquakes is we actually expect the braces to buckle. So one brace yields and the other brace buckles. When we push in the other direction, the brace that was just yielding now buckles, and the brace that was now buckling just yields. Okay, so again, you get this kind of response in a CBF. And so just as we did for SMRFs, we spend a lot of time trying to make sure that our weakest link or fuse in this case, which is the brace, is ductile. Okay, so for that, we will do things like enforce compactness limits, we'll do special considerations at the connections and so forth to make sure that the braces perform well. But in this case, the beams and columns are actually not expected to have inelastic action. And so we just have to design them to be stronger than the braces. Same idea, but a different system. In the US now, increasingly, buckling restrained brace frames are becoming common and popular. The idea here is that you have a steel core, which is like this. Essentially, it could be a flat plate. Sometimes it could be like in a cruciform shape. And the steel core is inside a concrete casing, which prevents the buckling of the steel core. And this is becoming extremely common in the US, especially in the West Coast. In fact, the first, I think, I'm going to say it was like at least maybe like 30-ish years ago, the first buckling restrained brace frame was designed in the US, which is actually on the UC Davis campus. But now they're all over the place, and we see a lot of these in the US. And the idea here is you have a steel core, and then you have this concrete casing. So when the brace actually goes into compression, it doesn't buckle, but it just kind of yields inside this core. It doesn't kind of buckle, so it just kind of squishes in, and when it pulls out, it yields. And as a result, you can get some pretty excellent performance because you don't get any buckling. And after an earthquake, if you want, you could just kind of replace this buckling restrained brace frame. Okay. And here are some examples of buckling restrained brace frames. The system started in Japan as a supplemental damping system, but in the United States, it's actually been adapted as an own structural system itself. So in fact, we'll put these kinds of buckling restrained braces in buildings where all the other connections are pin connections. So these BRBs, as we call them, are the primary lateral load carrying mechanism. Here's more examples of BRBs. They're extremely popular in the US nowadays. And here are some older BRBs in Japan. Okay, the way again we expect them to behave is, when you push to the right, instead of buckling like an SCBF, the BRB just yields in compression, whereas the other one just yields in tension. When the earthquake goes in the opposite direction, the one that was just yielding goes back into compression yielding rather than buckling, and then the other one starts yielding in tension. So again, they're just yielding back and forth. So this was kind of my little discussion or sort of talk about strength and ductility, the trade-offs, and talk a little bit more about moment frames and a little bit about concentrically braced frames and buckling restrained braced frames. And I'd like to close by talking about performance-based design in the US. Okay. So this is important because what the US code allows us to do now is that if we can demonstrate using other methods, okay, what we call code equivalence. In other words, if we can show using nonlinear dynamic analysis and some guidelines that I'm kind of listing on this page, that a structure is able to meet certain collapse probabilities. Remember, all the way back, I talked about meeting a certain probability of collapse. If we can kind of demonstrate that using nonlinear dynamic analysis, you can essentially ignore the code requirements. So in other words, the structure doesn't have to comply with the code. It can just completely ignore the code requirements as long as you can demonstrate doing this using nonlinear dynamic analysis. So you can show that the structure will not fall down. However, on the one hand, this is like, people might be like, wow, there's no code, right? So, but on the other hand, the idea is, you have to appoint a panel of experts, which we call a peer review committee. You have to spend a lot of money and effort doing these nonlinear dynamic analysis. But what we often find is that, especially for larger buildings, taller buildings, more expensive buildings, which can sometimes have costs of hundreds of millions of dollars, the amount of saving that you can do by quote unquote ignoring the code is much, much higher than the investment in doing some of these fancy analyses. Okay, so the idea is a lot of this performance-based analysis is currently being used to actually economize your structure, because we find that applying the code for each one of these structures actually tends to be very expensive. And if we can demonstrate by other means that the structure is equally good in terms of collapse performance, we can essentially like ignore the code and design the structure for a lot cheaper. So this is largely happening. In fact, I would say that a very large number of buildings in the United States, which are like, you know, mid to even high rises for sure, largely don't end up using the code or, you know, or the seismic provisions as they are, but they end up using performance-based demonstration of code equivalence. Okay, and there's like some of the documents here that I've showed which kind of talk about how to do that. Finally, ending here is that, you know, largely nowadays, even if the code and the performance based earthquake engineering has like kind of advanced, we're starting to talk a little bit more about things like resilience. When I say resilience, it means like reducing the downtime, reducing how long the building will be shut down, the cost of replacement, and so forth. But to be able to simulate them, measure them, and design for them. And that's something we talk about a lot. We're still not there wholesale in the US, but we're kind of gradually getting to that point. And then maybe in the next 10 or 15 years, you know, we might actually have some sort of resilience ideas built into our codes. But currently, we're still kind of not doing that. We're doing performance-based earthquake engineering mainly to kind of get around the code and have more economical building designs. This is my last slide, where I'm going to talk about some of the main takeaways that I'd like you all to have from this lecture. So the first one is that designing structures to yield and be damage tolerant, okay, results in tremendous savings in tonnage. So if you're worried about the cost of steel that you put in the building, the actual tons of steel, if you can make your structure more ductile, in an earthquake, you're actually going to require a lot less amount of steel. Okay, so that's why you need ductility. However, to make the structure more ductile, the devil is in the details. You need to have the welding right, the detailing, the quality control, all these things which seem like just arbitrary checks. They're actually the most important checks because they assure you the ductility, which can allow you to reduce the tonnage. Okay. And finally, any money that you spend on improving these saves you a lot of money in overall cost. Okay. And finally, the performance-based earthquake engineering, we're doing this quite a bit. It likely results in economy. Okay, but we're not all the way there in terms of like having resilience in our building codes. So with that, I'm going to sort of sign off, and I will be there to answer any questions that you would like.
Thank you, Professor Kanvinde. And with this, I would also like to welcome you to today's invited lecture. Thank you for your presentation. It was very informative, and I thoroughly enjoyed listening to you. I hope I'm audible to you.
Yeah, I can hear you. Yeah.
Yes. So now quickly we'll take up questions from our listeners, participants. And the very first question is from Mr. Krishna. He asked, the through thickness property of steel is very low compared to the length and width directions. Is it possible that the fracture in beam column joint at the wells have occurred due to this property? And next he clarifies the through thickness mentioned is that of the column flange to which the weld is made.
So yeah, thank you for the question. It's a really good question. You're right. The through thickness property is much lower as compared to the lengthwise properties. However, you know, there's been a lot of studies on this, and people have found that even though the toughness in the through thickness direction is lower, the demands tend to actually be highest at the weld where you have the pre-existing flaw. And so people have done a number of fracture mechanics studies to show that the root cause for the initiation of the fracture was actually the groove weld. Once the fracture starts out, you know, then it can propagate into various parts of the connection, and some of those failures, subsequent failures, have been through thickness propagation, but the through thickness properties generally are not blamed for the initiation of the fracture itself.
Okay, next is from Mr. Tamilinian Dhavamani. Is there any issue we need to think if we use American codes on welding and connections for Indian steel and welding electrodes?
Yes. So the answer is yes. So the thing is, there's a number of different standards, a number of different types of trainings, and everything that goes together in kind of coming together or building these connections. So for example, right from the electrode manufacturers to the development of the weld procedure, to pre-qualification of the connection, to training of the welders for different types of welds, all of these things need to be certified independently and then together in terms of a pre-qualified connection, so you can use that connection with confidence. So in other words, you can't just take an Indian electrode, take a welder who is not trained to weld a certain way, and then build a connection and hope that it will work. So all of these things need to be done to have the right performance.
Rightly said. Another question is from Mr. Nicholas Johansson. What is the maximum strain allowed in structural steel for the definition of the rotation capacity of a steel section?
So there is no real, there is no such thing as such. Typically, you'll have about 15% strain at which you start, to get ultimate stress in steel. But usually, when you think about a connection, what defines the rotation capacity is usually something like a fracture or local buckling. And we, rather than trying to calculate these capacities based on the local strains, we try to think of the capacity of the connection as a whole, because there are many other factors in addition to the local material strain capacity that go into actually determining the overall rotation capacity of the connection.
Well, then another interesting question is it safe to use moment releases for secondary beam connections while modeling a steel structure, as deep beams with shear connection might not totally be a pure shear connection?
So I guess when you say a secondary beam connections, does this mean gravity beams, I guess, out of plane? I'm not sure exactly what you mean by the secondary beam connection, but I guess all I can say is that if you're trying to design a special moment frame, all the connections should have a certain stiffness for it to be treated as a moment frame. If you don't have that stiffness, you cannot treat that connection as a certain as a moment resisting connection. And there's pretty strict guidelines on when the connection becomes a fully restrained connection versus what we call a partially restrained connection. And it has to do with the relative stiffness between the beam and the connection itself. And so I think if you don't meet those, then you can't call it a fully restrained connection.
Okay, another question is high seismic occurrence zone, the structure once reach in plastic zone, how is it to be analyzed for next seismic occurrence?
So this is usually not a part of the building code. What ends up happening is, we have standards, for example, which have to do with retrofit and repair of structures. For example, ASC 41 is one of those standards, and that provides a lot of guidance for the assessment of existing structures and their rehabilitation. But it doesn't necessarily kind of, lay down an exact procedure for how you actually analyze it for the next earthquakes. It's more like, when they need to be fixed and how you basically predict what it's going to be. So it's not like a full nonlinear dynamic analysis, but there are simplified procedures to analyze what the structure might do in subsequent earthquakes. And ASC 41 is a good location for that if you wanted to look.
Indeed, it is.
And also, by the way, AISC 342, ASC 41 and AISC 342 are the two documents that you want to look at.
Yes. Another question is, could a tune mass damper, which is calibrated to the fundamental mode of vibration in order to mitigate wind-induced vibration for a high-rise building, be efficient for a seismic load?
I'm guessing I'm not. So this is not, again, damping systems are not my expertise, so I don't want to comment on it. My understanding is yes. if you put enough money into it, anything can be made efficient. But again, this is not my expertise, so I don't want to say anything here.
Okay, so we are getting a lot of questions here. Quickly, we can catch up. Could you elaborate more on connection failure of beam column connection under Northridge earthquake? Because it was it because of higher yield strength of beam, or was there any other cause except welding property?
It was a combination. So, so the higher yield strength of the beams was one, which sort of increased the demands in the welds. The local detailing, the backing bars, the flaws in that region was another problem. The weld quality and toughness itself was another problem because the welds, typically had Sharpie V-notch values in the range of 5 to 10 foot-pounds. We typically expend at least 20 or more nowadays. In addition to all this, there are also some connection design factors which I didn't get into the lecture. For example, before Northridge, we used to use bolted shear tabs rather than welded shear tabs. And this would increase the amount of shear actually going through the flanges because the shear tabs don't provide a very stiff load path for the shear in the web, and that increases the demand on the flanges. So there's actually a range of these different things that all kind of added up together at this one location at the bottom of the flange, increasing the fracture toughness demands.
Okay, so I think we'll take one last question, and I request after that to all the participants who would like to communicate with you, they can message to us on the SSEF forum directly, and then we can forward you the queries.
Okay.
So yes, so the last question will be from Mr. Tamil Selvan. While selecting weld electrode to be used for welding near connections, how we have to select it, whether we have to go for overmatching or balanced kind of weld electrode. If we are selecting high, I'm just continuing the question. If we are selecting very high over strength electrode, it may have less ductility. And so how do we address this issue?
So we usually overmatch. So, a standard steel grade in the US is 50 KSI, which is about 345 megapascals. And so we'll use a 70 KSI electrode in almost all cases. And we have electrodes that are specially formulated nowadays, which at 70 KSI have significant ductility that we need. So we should use electrodes which are overmatched. We certainly don't want failure in the weld itself. And we are able to find electrodes that are overmatched and still have the ductility that we require.
Okay, thank you. If you are free, then we can take up one or two more questions.
I'm happy to take more questions, yeah.
Okay, so another one, dear sir, how size reduces hugely when we give consideration for ductility against lateral loading? We initially design every structure to take gravity loading. The initial size of structure is initially defined, which can already be very huge, can't compromise with them. The R factor might just affect the minor size differences above the initial design, which is for the which is higher for a higher height and similar size requirement for earthquake. That might be required for just additional lateral load.
So you're right, and so you're right to a very large extent. But here are the two key differences. I think this might have to do with some differences between standard Indian construction practice and the U.S. construction practice, and also the hazard. So, for example, where I live in California, the seismic hazard is extremely high, even compared to some of the highest zones in India. It tends to be pretty high there. So that's one effect. So the difference between gravity and seismic is high. The second thing is often we try to separate the gravity loads from the seismic loads to the extent we can. So we have a different gravity framing system than a seismic system. So if you think about a typical moment frame in the US, and if you think about how much gravity load it's actually carrying, it's pretty low. So, for example, if you think about a column in a moment frame in the US, it's usually carrying about, I would say, somewhere around 20 to 30% of its axial load capacity under gravity load, and the rest of it all ends up coming from the seismic load. So, so again, when you're looking on the east coast of the US where you have low seismicity and so forth, the R factors, again, we don't end up using a more special moment frame there. We actually end up using a low R factor exactly for the reasons you mentioned, because there isn't that much of a benefit to be gained. But especially in high seismic zones with perimeter systems, we find that we reduce the size tremendously.
Okay, so another question from Mr. Nicholas Johansson. Could the plastic hinges appearing in the structure affect the eigenperiod of the structure, giving a longer period with a larger deformation demand?
Yes, that is true. And the thing is, we consider this in various different kinds of ways. So, a lot of the design code factors, such as the R factor, the other CD factors, and so forth, are based on nonlinear time history simulations, which actually consider this. And there's also other aspects that we use this kind of information is in how we kind of scale ground motions. We kind of consider things like period elongation, which changes the dynamic response of the structure, which might happen differently at different levels of intensity and so forth. So what you're saying is actually considered in formulating the design procedure. So, sort of the example, so the description that I gave in my lecture was a very simplified sort of design procedure, but the design procedure is the result of considering all of these effects that you're talking about.
Okay, again, I would like to thank you for taking out time for this lecture today. And I would like to thank all the participants who were present today. And I would request them to kindly send their queries and questions regarding today's lecture on SSEF forum, and we shall be replying. We shall be sharing them with Professor Kanvinde as well. Thank you, sir, so much. It was very nice listening to you.
Thank you. Bye.